So the first part of this video was actually leading up to this topic that we'll talk about in this PowerPoint, which is the topic of sampling distributions. This is an important topic to help us understand the theory behind using data from a sample to reach a conclusion about the population it comes from. First, we need to talk about the idea of sampling variability. Sampling variability is just the fact that different samples give different results. We've already seen sampling variability in the first part of this video because we saw that when you take different samples from a population, the sample mean doesn't always come out to the same number. It changes from one sample to the next. The next term that we'll cover is called a sampling distribution, which is a collection of outcomes calculated with all possible samples of a certain size. And I'll give you some examples of creating sampling distributions. But first, I wanted to start with giving you one more demonstration just to help you get the general idea of what a sampling distribution is. So this simulation is just meant to teach you the idea of a sampling distribution, not how to actually create one. So let's imagine that these are the exam scores of 72 students in a class. It's a population of 72 students, and I wanted to create a sampling distribution of all possible samples of 3 people. What I would need to do is I would need to calculate the mean of every possible sample of 3 people that could be selected from the population. Meaning I would have to calculate the mean of every possible combination of 3 people that could be chosen from the population. And then, once I calculated all of those sample means, I would have the collection of the means of all possible samples of 3 people, and that collection of sample means would be a sampling distribution. So let's think about what are the possible samples of 3 people. Well, here's one possible sample, and it has a sample mean. I should have put an X bar because it's a sample mean, but I just used an X instead. Here's a different possible sample of 3 people, and it has its own sample mean. Here's a different one. Here's one more. So there's all these different possible samples of 3 people that could be selected from the population, and each possible sample has its own sample mean. Some of the possible samples have the same sample mean, and those sample means end up being stacked above each other. For example, these 2 samples both have the same sample mean. Here's another one. All 3 of these samples had a sample mean of 81.7. So what we're actually looking at here is the possible samples that could be selected if someone randomly selected a sample of 3 people from this population. So if a person randomly selected a sample of 3 people from this population, recorded their exam scores, and calculated the mean of the sample, the person would get one of these sample means inside of here. For example, the person might get this sample mean, the person might get this sample mean, the person might get this sample mean right here. Each of these X's is just the mean of a different possible sample of 3 people that could be chosen. So if I get this sample, if I randomly select a sample of 3 people and I end up getting this sample, my sample mean will be about 76. If I randomly select 3 people and I end up getting this sample, my sample mean will be 80. If I get this sample, my sample mean will also be 80. And if I get this sample, my sample mean will also be 80, because all 3 of these possible samples all have a mean of 80. If I get this sample right here, my sample mean will be about 84. So we're just looking at the means of all possible samples that could be selected when a person is selecting a sample of 3 people from the population. Now, there's actually many possible samples of 3 people that could be selected. So I'm not going to be able to calculate the means of all of them. But I want you to understand the idea that if I did calculate the means of all possible samples of 3 people and plotted them here, it would be the sampling distribution of the means of all possible samples of 3 people. And actually, every possible sample has its own sampling distribution, because if I selected a sample of 4 people from this population, my sample would be one of the possible samples of 4 people inside of the sampling distribution of all possible samples of 4 people. If I randomly selected a sample of 10 people from this population, my sample would be one of the possible samples of 10 people inside of the sampling distribution of all possible samples of 10. And the idea of a sampling distribution is important because it shows which sample means are more likely to be found and which sample means are less likely to be found. We can see that if we look at the sampling distribution that's starting to build up here, we can see that the sample means, most of the possible samples have sample means near the population mean, and fewer of the possible samples have sample means further away from the population mean. That means that if a researcher is randomly selecting a sample from a population and calculating the sample mean, the researcher has a good chance of getting a sample mean within a certain range of the population mean that they're trying to estimate. And they're less likely to have a sample mean that's extreme and really inaccurate. So we talked about this idea that when a researcher randomly selects a sample and calculates the sample mean tends to estimate the population mean at least fairly well, meaning the sample mean tends to fall fairly close to the population mean. The reason why that happens is because of the shape of the sampling distribution. So if I wanted to look at all possible samples of 10 people, well, I would need to calculate the means of all possible samples of 10. Sorry, I'll back up a little bit. Here's one possible sample of 10 people that could be chosen. So if I selected a sample of 10 people randomly, and I end up getting this sample, then my sample mean will end up being 80.2. If I end up getting these 10 people, my sample mean will end up being 81, right there. If I get these 10 people, my sample mean will be 82.2, right there. If I get these 10 people, my sample mean will be 78.9. So notice how when you're selecting a bigger sample size, the possible samples have sample means closer to the population mean. Almost all of the possible samples have sample means really close to the population mean of 80. Because remember, larger samples are more accurate. They more accurately estimate the population mean. So when you take a bigger sample from a population, when you calculate the sample mean to estimate the population mean, the possible samples that could end up being selected have sample means that are closer in to the population mean. In other words, the possible samples have accurate sample means. If I get this sample, it'll be pretty accurate. If I get this sample, it'll be pretty accurate. And if I get this sample, it'll be pretty accurate. So when you take a bigger sample from a population, the possible samples move in toward the population mean, and they all tend to have sample means closer to the population mean. That's why a researcher who uses a bigger sample size is likely to get a sample mean closer to the population mean and get a more accurate result. And later on, we'll talk more about how spread out these possible samples are from each other. There's actually a word that's used. There's actually a term for the amount of dispersion that's in the possible samples. When it's called the standard error. When the sampling distribution has high dispersion, meaning the possible samples have sample means that are spread out far away from each other, then the standard error is high. If the possible samples have sample means that are really close to each other, like we see here, the standard error is low. We'll talk more about that a little bit later. First, we need to cover a term called the central limit theorem, which is really just a technical word for something we've already talked about. The central limit theorem says that if the population has a normal distribution, the sampling distribution is always normal. And if the population is skewed, the sampling distribution is skewed just like the population with a small sample size, but is roughly normal with a large sample size. So if the population is normal, the sampling distribution is always normal, no matter what sample size you're talking about, or no matter what sample size you're dealing with. If the population is skewed, the sampling distribution is skewed when you're using a small sample size, but is roughly normal with a large sample size, a 30 or larger. And I wanted to mention something that tends to cause confusion when people first learn about the idea of a sampling distribution. When students think about the idea of a sampling distribution, they tend to think of it as the distribution of the people inside of a sample. So students tend to think that if you take a sample from a population, then the people inside of the selected sample follow the sampling distribution. They think that it's the distribution of the members of people inside of a certain sample, but that's actually not true. It's not. A sampling distribution isn't a distribution of people. It's actually a distribution of outcomes, or it's actually a distribution of possible samples. So if you take a sample from a population and you take a certain number of individual people from the population and you calculate the mean of that group of that sample mean that you've calculated is actually one building block of the sampling distribution. It's just one building block inside here somewhere. So it's actually a distribution made up of all possible samples that could be selected, and each sample is just a building block stacked above its sample mean. So all of the if this right here is, let's say, 70 on the number line, all of the sample means, I'm sorry, all of the possible samples that have a sample mean of 70 will all be stacked above each other right here. If this is 80, all of the possible samples with sample means of 80 will all be stacked above each other right here. And I'll show you. I'll actually show you a quick demonstration with the website to explain this idea of a sampling distribution.